Asynchronous replication is fast. Writes complete at leader speed without waiting for followers. But there's a cost that only becomes visible when you look at what a follower sees in the moment after a write. If you write a value to the leader and immediately read it from a follower, the follower may not have applied the write yet. You sent the write half a second ago. The replication lag is 400 milliseconds. Your read returns the old value. Under normal conditions, a lightly loaded system, a fast network replication lag is typically a fraction of a second. So small you'd never notice. But when the system is under heavy write load, when the network is congested, or when a follower falls behind during a maintenance operation, replication lag can grow to seconds or even minutes. This behavior is called eventual consistency. The book defines it precisely. If you stop writing to the database, eventually all reads will return the same value. The followers will eventually catch up to the leader. But eventually provides no bound on how long that takes. It could be milliseconds, it could be minutes. The contrast is with stronger consistency guarantees. Synchronous replication provides read-after-write consistency. If a write succeeded, any subsequent read will see it. Eventual consistency provides no such guarantee. A client can write data and immediately read stale data from a follower. For many applications, eventual consistency is acceptable. Users refreshing a social feed who see a post appear a second late don't notice. But for other behaviors, even brief lag creates genuinely incorrect experiences that feel like bugs. The book identifies 3 specific problems that arise from replication lag. Each one has a name, and each name describes a specific guarantee you might want to provide. Understanding these 3 guarantees helps you design applications that work correctly even under lag. Here's a scenario that happens constantly in real applications and produces a jarring experience when it goes wrong. A user submits a comment on a blog post. The write goes to the leader. The user's browser immediately requests the page again, to show the updated comments section. The request is routed to a follower which hasn't yet received the new comment from the leader. The page loads without the comment the user just submitted. From the user's perspective, their comment disappeared. This isn't a theoretical edge case. It's a frequent occurrence in systems with read replicas and even a small amount of replication lag. The user who submitted the data is the person most likely to immediately read back the same data. The guarantee that prevents this is called read your writes consistency, also called read after write consistency. It means a user will always see the data they themselves just wrote. They might see stale data written by other users, but their own writes are immediately visible to them. How do you implement read your writes consistency in a leader-follower system? The book gives several practical techniques. One approach: when reading something a user may have recently modified, read from the leader. For example, a user's own profile is always read from the leader. Other users' profiles can be served from followers. Another approach: track the timestamp of the user's last write. For some time window after a write, say 1 minute, route all reads for that user to the leader. After the window expires, the follower has likely caught up and reads can go there. A more precise version: record the replication log position of the last write. Route reads to any replica that has applied at least up to that position. Only when no such replica is available do you fall back to the leader. These techniques work for a single device. But if the same user is logged in on a phone and a laptop simultaneously, a write on the phone might not be visible on the laptop if the laptop's reads go to a different replica. Cross-device read your writes consistency requires centralized tracking of the user's last write position, not per device. Here's a problem subtler than missing your own writes, but equally jarring to users. Imagine a user makes 2 requests in quick succession. The first request goes to a replica that is 5 seconds behind the leader. They see recent data. The second request, milliseconds later, goes to a replica that is 2 minutes behind the leader. They see much older data. Time appears to go backwards. A concrete example: a user views a comment thread. Their first request shows 3 comments, one of which is a reply posted 30 seconds ago. Their second request, refreshing the page, goes to a different replica. That replica hasn't yet received the reply. The comment thread shows 2 comments. The reply that existed a moment ago has apparently vanished. Then on the third refresh, the reply reappears. The guarantee that prevents this is called monotonic reads. It means, if a user has previously read some value, a subsequent read will not return an older value. The user will never move backward in time. Monotonic reads is a weaker guarantee than strong consistency. Users might still see data that's seconds or minutes behind the leader. But they won't see data that regresses. Once you've seen the comment reply, you'll always see it going forward. The implementation is straightforward: route each user's reads to the same replica. Hash the user ID to select a replica, and route all reads for that user to that replica. If that replica fails, the user's reads are rerouted to a different replica, but that may cause a brief monotonicity violation during the failover period. This is the distinction between monotonic reads and read your writes. Monotonic reads guarantees that reads don't go backward in time for any data. Read your writes guarantees that a user's own writes are visible to themselves. A system can provide one without the other. There's a third type of anomaly that emerges under replication lag, and this one is particularly insidious because it makes causally related events appear to happen in the wrong order. The book's example is memorable. Imagine a conversation between two people, Mr. Poons and Mrs. Cake, playing out in a database. Mr. Poons asks a question, "How far into the future can you see?" Mrs. Cake answers, "About 10 seconds usually." A third observer reads from a replica. Due to replication lag, they see Mrs. Cake's answer before they see Mr. Poons's question. The answer appears first, and makes no sense without the question. From the observer's perspective, Mrs. Cake seems to be predicting questions rather than answering them. This sounds contrived, but it maps to real problems. Consider an event sourcing system where payment authorized must always appear before payment captured. Or a system where a configuration change must appear before the events that depend on it. If the replication log applies writes in an order that violates causal dependencies, observers see a world that doesn't make sense. The guarantee that prevents this is called consistent prefix reads. It means, if a sequence of writes happened in a certain order, anyone reading those writes will see them in the same order. Causally related events are never observed out of sequence. Consistent prefix reads is particularly difficult to guarantee in sharded databases, where different partitions are replicated independently. A write to partition A and a causally subsequent write to partition B may be replicated at different speeds. An observer reading from both partitions might see the partition B write before the partition A write. The solution requires tracking causality, specifically, which writes happen before which other writes, and ensuring the replication system respects those dependencies. Causality tracking is complex, and we'll encounter it again in the chapter on transactions. All three of these guarantees, read your writes, monotonic reads, and consistent prefix reads, can be provided by a carefully designed single-leader replication system. But they all require additional complexity beyond simple asynchronous replication. The question of whether you need them depends entirely on your application's behavior.